Okay, so Junyoung realizes the surface area will not be the same. So of the cuboid will not be the same as the cube unless he changes the height. So he's changed the height to 10 centimeters, but he's also still trying to subtract a number and add a number to the other two dimensions. So, part 1. So if the surface area of the cube is the same as the surface area of the cuboid, show that this equation holds. So for the surface areas to be the same, they must equal each other, right? And then that'll give us an equation, and then that'll boil down to this equation. So we're reminded that the surface area of a cube of all sides p has a surface area of 6p squared, right? Each face is p times p, like the square, and there are 6 faces, so it has an area of 6p squared. We can find our own expression for surface area of this cube on its 6 faces. Add them all up, and then equate that to 6p squared. So let's do that now. So surface area of the cuboid is, let's do this darker face first, so that's p minus a times 10, or I'll just write that as 10 times p minus a. And it's a little bit hard in 3D, but we know that there is another face sort of behind this cube that we can't see. And in fact, each of these faces, there are 2 of them. So what I'm going to do is just put a 2 out the front. Right, so this says there's 2 faces that have an area of 10 times p minus a. So we've got those ones done already. And to that we will add, let's do this lighter grey, this front face here, which is 10 times p plus a. And again, there's 2 of them, right? There's one at the back that we can't see. And then this top, this lightest grey one, is p minus a times p plus a. And again, there's 2 of them, one on the bottom that we can't see. So that is the surface area of the cuboid. Let's expand it out, simplify it. So we're left with 10p minus 10a plus 10p plus 10a plus p squared minus ap, plus ap minus ap, so they will cancel, minus a squared. Minus 10a plus 10a, we're left with 20p plus p squared minus a squared, which equals 2p squared plus 40p minus 2a squared. And now, that whole expression will equal 6p squared. Right, so we're equating the surface area of the cuboid to the surface area of the cube. And the question is asking us to show that this equation holds. So let's just take everything to one side. In this case, since the p squared coefficient is positive, I'll actually take everything to the left. So 6p squared minus 2p squared, 4p squared, and then minus 40p minus negative 2a, so plus 2a squared, equals 0. Okay, it's looking pretty close, but I see that we could divide everything by 2. And then we're left with that equation. So what this says is if we want the surface area of the cuboid to equal the surface area of the cube, this relationship must be true for P and A. Okay, part 2. We're asked to use the discriminant to find the largest possible whole number that A could be for the surface area of the cube to equal the surface area of the cuboid. And then using this value of A, this whole number, find the dimensions of the cube and the cuboid. Now this one's a little bit tricky because there's also that unknown P. So we're going to need to find the maximum value of A and then solve for P, right? Because this is just a quadratic. So once we have A, we can solve for P. But that's an extra step to be aware of. Okay, well let's just start with the discriminant. So remember that's B squared minus 4AC, where A is 2, B is negative 20, and C is plus A squared. And for there to be valid solutions, we want the discriminant to be positive, right? Greater than 0. So let's plug in A, B, and C. So remember, B is just the number in front of the variable. In this case, the variable is P. So minus 20 squared minus 4 times A, which is 2, times C, which is A squared, greater than 0, which is minus 20 squared is 400, minus 8A squared. Then we could add 8A squared to both sides, divide both sides. So if A squared is less than 50, so this is 50, A squared is less than 50, it means it's between negative root 50 and positive root 50. Right, so I just drew a quadratic like A squared, simple quadratic. I drew the horizontal line y equals 50, or A equals 50 in this case, and then just reason that if A is between these intersections, it's less, as opposed to outside of the intersections. But can A be a negative number? Guess it could. Right, that just means the direction's different. Yeah, so we could have it as a negative number, or we could just simplify it to just the positives. Like, it doesn't change the problem at all. So let's just go for this one, keep it simple. And root 50 is approximately 7.1. And remember, the question is asking us the largest possible whole number. Okay, so let's try 7, I guess, right? So we could try A equals 7, because that's a whole number. and it's as big as it'll get within our range. Now we just need to see that it works in this context. So let's substitute in our value for a into this quadratic and solve for p, and then test that that solution for p is meaningful, right? If it's has a negative value or just doesn't make sense, then we need to try a different value for a. So we have 2p squared minus 20p plus a squared, right, where a squared in this case will be 49, equals 0. I won't bore you with solving this, so just use polysolve on your calculator, and we find p equals 5.707 or 4.293. Okay, and remember the cuboid, it was p minus a, p plus a, was that. So let's substitute in the values for p and a. So this width here at the front, 5.7 minus 7, so that's a negative value. Or 4.293 minus 7, also a negative value. Right, so I'm just looking at this side, and I'm substituting in either p and our value for a. And since both values of p give us a negative value, it makes me think the solution isn't meaningful in this context. So therefore, or rather, p minus a is 5.707 minus 7, which is less than 0 for a equals 7, not a solution. Right, so just to summarize what we've done so far, we used the discriminant to find the possible values of a for there to be a solution. We picked the largest whole number in that range, which is 7, but we tried to verify it in the context. However, in this context, it didn't make much sense because we got a negative dimension for p minus a, so we discarded that solution. So what we do next is we find the next largest whole number, and in this case a equals 6, right? We just go 1 down. We repeat the same process, so 2p squared minus 20p plus a squared 36 equals 0. Use polysolve or graph it and find p equals 7.646 or p equals 2.354. Now, looking at the dimensions, p minus a will be, well, we have two p values to choose from. If we picked a smaller one, we'd run into the same problem, right? We'd get a negative dimension. But if we chose 7.646 minus 6, we would get a positive number, right? 1.646. Therefore, a equals 6 is a valid solution. In that it makes sense in this context, and since the discriminant was positive at the start, we know the surface areas of the cube and the cuboid would be the same for these particular values of p. So, with that said, the value for p was 7.646, right, which gives us the dimensions of the cube. All sides are of length p, and then the cuboid will have dimensions p minus a, which we worked out as 1.646, p plus a, which is 7.646 plus 6, which is 13.646, and a height of 10. Is it in centimeters? Yeah, centimeters.